Hello everyone, in this video we're going to go over the week 6 worksheet solutions. So in the first question we had, find the fourth term of the sequence, and we have that we have a sequence that is given in terms of the first term, the second term, and then they give me the n term in terms of the two terms that come before. So with that I can actually go ahead and get a3, because a3 is just going to be twice a2 minus a1. Since plugging 3 in n is going to produce those values here. Now because I have that a2 is 1 and a1 is 1, this is just 2 times 1 minus 1, and I'm also going to have that this is 1. Now for a4, I'm going to get a similar situation. Then I get 2a3 minus a2, and then again, because a3 is 1, this is 2 times 1 minus 1, and is 1 again. So this is the fourth term for these sequences. In general, because the difference is 2 and I seems to be getting always 1, it seems like I'm gonna be getting 1 all the time. Now for B, we have that the sequence is n factorial. And this goes from n equals 0 to infinity, so we can actually put a0. a0 is 0 factorial, which is actually 1. a1 is 1 factorial, which is 1 as well. a2 is 2 factorial, and 2 factorial is the multiplication of 1 times 2, which is 2. a3 is 3 factorial, and that will be 1 times 2 times 3. So that'll be 6. And let's do a4 just for the sake of clarity. This is 1 times 2 times 3 times 4. That is what 4 factorial is, which is 24. Okay. Now question number 2 is about whether the sequence converges, and if it converges, what it converges to. So the first one is kind of hard to measure up what it does. Clearly, if I have 1 plus 9 to the n, that's going to be bigger than 9 to the n. And so 1 plus 9 to the n is less than 9 to the n. And then I can put the 4 to the n next in each of these pieces. Now notice that this is less than this. So if I prove that this is convergent, then this is going to be convergent. Now this is a geometric series. Or sorry, a geometric sequence, and so the limit when n goes to infinity of 4 over 9 to the n, because this number is less than 1, then this is going to go to 0. And so hence, because this is also a positive sequence bigger than 0, by squeeze theorem, then I'm going to have that the limit when n goes to infinity of 4 to the n over 1 plus 9 to the n is equal to 0. In question B, I have a root of this factor, and I can probably simplify this a bit. I can rewrite this as divided by n squared on everywhere. So this is 1n squared plus 9. And below this will be 1 over n squared plus 1, and notice that this will be like factoring out n squared top and bottom. So this is here, and I can kind of cancel out this term. So if I'm going to take a limit when n goes to infinity of a n here, this is equivalent just to doing the root of the limit when n goes to infinity of 1 over n squared plus 9 over 1 over n squared plus 1. And so this clearly is going to go to square root of 9 over 1 or 3. Now for C, we have limit when n goes to infinity of this situation. Here we don't have the root, but what we can do to simplify that is actually make a square here, so we can have the root. So what do I mean by that? Well, this will be 1 plus 9 n square, and below I'm going to have 1 plus n square. So now I can cover everything with the root. Of course, I can transition that to limit when n goes to infinity of 1 plus 9n square. And this bottom here is going to be 1 plus 2n square plus n to the 4. Now, immediately, because the bottom is going to infinity much more faster than the top, this is going to go to 0. And so that's the limit for this sequence. Now for D, what we do is we're going to divide by whatever is the dominant term in the denominator. So in this case, the largest term, or the dominant term in the denominator, is going to be 3 to the n, since that's going to be much more faster growing than n to the 1000. And we can see this as n cubed over 3 to the n plus pi to the n over 3 to the n over n to the 1000 over 3 to the n plus 1. And so now notice that I just divided up and down by 3 to the n, and this term, when n goes to infinity, so if n goes to infinity, this piece goes to 0 because 3 to the n grows faster. This piece goes to 0 as well because 3 to the n goes faster. And so this is going towards 1 on the bottom. But on the top, pi to the n actually grows faster than 3 to the n, since pi is a little bit more than 3. So this is going to go to infinity. And that's it. And this is a divergent sequence. Now in E, what we do is we use a little bit of the properties of the log, and we see an as log of n times log of 2 plus log of n. And so we can divide by log of n to simplify a little bit how this looks like, and we're going to get this. And now when n goes to infinity, then you can see that this term goes to 0 and everything else goes to 1. For F, we have a ratio of factorials, but 2n plus 1 factorial can be really seen as 2n minus 1 factorial times 2n times 2n plus 1. And of course, because we're dividing by 2n minus 1 factorial, that's going to create a factor that we can actually cancel out. And so at the very end, that ratio is just going to transform my sequence into 2n over times 2n plus 1. And that's going to infinity if n goes to infinity. So this is a divergent sequence. Now let's transition to series. So the first series is going to be an example of a complicated geometric series. If you remember, the geometric series is when n equals 0 of a r to the n. This can be seen as the sequence a 1 minus r to the n over 1 minus r. So this is the sum that relates to this. But in this scenario, we have n equals 3, so we gotta fix first that, so it starts from 0. So I'm gonna make a change on the value. So I'm gonna say k plus 3 is gonna be equals to n. And so in that sense, if I do that, then k becomes really n minus 3. If n starts from 3, now k is going to start from 0, and so this series is going to transform into the series of k equals 0 to infinity, and now I'm going to be replacing wherever n was. I'm going to be replacing it by k plus 3. So this is 8, 1 minus k plus 3. And this is going to be 5 to the plus 5 to the 2 plus k plus 3. So now if I simplify a bit, this is really 8 to the minus k, and then from minus 3 and 1 I get 8 to the 2, 8 to the minus 2, and over here I get 5 to the 5, and I get 5 to the k. So now I can remove whatever doesn't have a k on it, and so this is essentially 5 to the 5 times or over a square, sum from k equals 0 to infinity of 5 over 8 to the k. And so now this is exactly something that we can transform into this geometric series. And so this is 5 to the 5 a square, and it's going to be 1 minus 5 over 8 to the n over 1 minus 5 to the 5 over 8. And so when n goes to infinity, then we have that this goes towards 0, since the ratio here 5 over 8 is less than 1. And then we're going to have this is 5 to the 5 over, and this is 8 over 8 minus 5 over 8, so it's 3 over 8. So over here we're gonna have 3 over 8, and then times a square here. So we can see this as 5 to the 5 over 24. And that will be the sum of number 3. Now number 4 says that if an diverges and bn diverges, then must the sum of the series diverge, and if it can converge, give an example of a specific sequence a and bn to make this happen. So you can kind of get this example very easily if you consider something that can be a telescopic sequence. So for example, let's just take 1 over n plus 1 that we know is divergent, and well, let's take 1 over n or minus 1 over n for the sake of the argument. Now easily individually each of this is divergent, but now if I take the sum, then this is going to be a telescopic series, and this is going to be equals to the limit when n goes to infinity of 1/2 minus 1 over n. Think so. Let me see. This is 1/2 minus 1 plus, and n equals 2 is 1/3 minus 1/2. It's actually, sorry, minus 1 here. So it will be minus 1 plus 1 over n, and so this sum is equals to minus 1. So this will be a convergent series. So it doesn't necessarily have to be a sum of two divergent series. It's not necessarily divergent. Now, for the last series of the worksheet, we have to kind of check if the series 1 over n times n plus 1 over n plus 2 converges, and if it does, to find the sum. And this is likely a convergent series, especially because it has a lot of different things in here. So it's a big power. This is 1 over n squared plus n times n plus 2. So I kind of find it difficult to find the sum, probably, but this is going to be 1 over n cubed plus n squared plus 2n so n cubed plus 2n n squared let me rearrange this. So n cubed plus 2n squared, we're multiplying n squared by this part, and now plus n squared plus 2n. And so at the very end, this is just 1 over n cubed plus 3n squared plus 2n. So we can see the series as this. There's not an easy way to find convergency by this, so we're gonna have to use a tool of comparison with other type of series. So notice that n cubed plus 3n squared plus 2n, this is going to be larger than n cubed itself. And so because of that, we're going to have this. And so now we can compare it with this series, and because this series is going to be convergent, then this series is going to be convergent. And pretty much that's the end of that. There might be a specific way of approximating this numerically, but there isn't really a way to find necessarily the sum. And with the information that we might have, we might be able to just get telescopic from here. But we'll have to break this apart into two telescopic series. So this might be another way. Let me see if that's possible. So 1 over n plus 1, n plus 2 can be probably seen by partial fractions as a over n plus b over n plus 1 plus c over n plus 2. And so this, now we gotta find the partial fractions. So this is a by n plus 1, n plus 2 plus b and n plus 2 plus c in n plus 1. So if let's say n is equals 0, assuming that n is real numbers, we're going to have that 1 is equals to, this is going to go away in those two cases, and then we're going to have 2a. So we can have that a is equals 1/2. Now if n is equals -1, then this goes away, and we get this one. And then this gets me a 1, and this gets me a minus b. So 1 is equals to minus b, or b is equals -1. And finally, if n is equals -2, then you can remove this 2 from here, this one too, and only gonna be left with this. And 1 is gonna be equals to -2 times, and over here -1. So this is 2, so c is equals 1/2 2. So because of that, then we can see this arrangement as 1/2 1/n, and then b is -1, so -1/n plus 1, and then plus 1/2 1/n plus 1. But what we want to do is we want to find a way of getting telescopic series, so we're able to pry this apart. So we're gonna split this one as 1/2 plus 1/2. And so this means that we can really see this as 1/2 n minus 1/2 1/n plus 1. And then plus 1/2 1/2 1/n plus 2 minus 1/2 1/n plus 1. So in that way, the series of 1/n, n plus 1, n plus 2 can be seen as the limit when n goes to infinity, or let me just split this into two series, and the sum of two telescopic series. The sum of n equals 1 to infinity of, and I'm going to use a 1/2 here. So this is 1/n minus 1/n plus 1 plus 1/2 n equals 1 to infinity 1/n plus 2 minus 1 over n plus 1. And so as you can see, these are two telescopic series. And then we can split this apart as 1/2 the limit when n goes to infinity of plugging in the first term, which is 1 here, minus 1 over n plus 1, and then plus 1/2 limit when n goes to infinity of plugging in 1, I'm going to get minus 1/2 plus 1 over n plus 2. And as you can see, now when I take the limits, the actual limits, this is going to go to 0, this is going to go to 0. So this is 1/2 here. And this part here is going to be minus 1 over 4. So overall, this whole series is going to be equals to 1 over 4 in the sum. And so that's the end of the solutions for the week 6.